If there were no Niels Bohr, then there would be no Erwin Schrödinger, no Werner Heisenberg, no Paul Dirac, no Max Born, no Pauli, and no C.V. Raman. Because this mere idea of quantum jumps, it was work of a genius. Let's check it out. Exactly. The Bohr model formed the very foundation of quantum mechanics with the very fundamental idea of electron jumps. The electron jumps from higher energy level to lower energy level, gives out light with specific wavelength. Like in hydrogen atom, the electron jumps to the first electron shell, gives out ultraviolet light, which is known as Lemon series, or jump to the second electron shell, gives out visible light, which is known as Balmer series, or jump to the third electron shell, gives out infrared Paschen series, and so on. Yeah, before we go deep into the theory, let's check the different spectral lines with help of various spectrum tubes. And let us also try to resolve those spectral lines with spectroscope and diffraction gratings, the quantum mechanics in action, and let's check out the signatures of different atoms. Before we look at the spectra of different elements, let's check out the full spectrum of white light with diffraction grating. We get the entire Vibjor spectrum.
So let's begin with the most celebrated neon spectrum. Neon, an inert gas with atomic number 10, and here is the celebrated red glow of neon. If we look at this spectrum, we can find the multiple red lines with their wavelengths between 630 to 700 nanometers, and also there is one characteristic yellow line at 588 nanometers. But these multiple red lines which we found in the neon sign lamps, this characteristic red lines of neon make our cities glow in the night. Now let us compare the neon spectrum with that of argon, another inert gas with atomic number 18. If we look at the argon spectrum, we find similar red lines. However, we can easily differentiate it from the neon because that characteristic yellow line of neon with wavelength 588 nanometers, that is missing from the argon spectrum. Let's check out the simplest one, hydrogen spectrum. The visible lines in hydrogen emission spectrum constitute the Balmer series, named after Johann Balmer. The Balmer series mainly consists of 4 typical lines: a red one, a bluish green emission line, one blue line, and a violet line. This emission in visible spectrum occurs when the electron jumps from higher energy level to second energy level. The 4 lines in Balmer series consist of 656 nanometers, 486, 434, and 410 nanometer wavelengths. The red line with wavelength 656 nanometers is also known as H alpha or hydrogen alpha line. It is emitted when the electron jumps from third to second electron shell. Similarly, three other lines, hydrogen beta, gamma and delta lines, are emitted when the electron jumps to second energy level from the fourth, fifth and sixth energy levels respectively. Here is another hydrogen spectrum tube, and there is an interesting story behind this entire hydrogen spectrum lines. A primary school teacher called Johann Balmer had given an empirical formula to explain this visible spectrum of hydrogen atom. Then this formula was generalized for other series in hydrogen spectrum as a Rydberg formula, and these formulae were given the firm theoretical basis in the much celebrated Bohr's model of hydrogen atom. We will see the Bohr's model in theoretical details. Here is the celebrated hydrogen spectrum lines. And now let's check the spectrum of helium, the element of sun. Hence, it has been named after sun, the Helios, because it was first observed in the sun. The helium spectrum is bit more complex than that of hydrogen because it has couple of electrons. The four lines are clearly visible in the helium spectrum: the purple, blue line, yellow and a red line. Characteristic four lines of the helium spectrum, and we can see the most prominent characteristic yellow line with wavelength 587.6 nanometers. This yellow line is the signature of helium. Now let's take a look at very characteristic spectrum of element mercury. Here we can see a drop of elemental mercury. When high voltage is applied, this elemental mercury evaporates and gives out the typical mercury emission spectra. And this is how the quite famous mercury vapor lamp works. Let's check out the characteristic mercury spectra. Here it is. We can see the characteristic emission lines from mercury, the typical green and yellow lines. There are also blue and violet lines, but the most characteristic is the green line with wavelength 546 nanometers and a couple of yellow lines having their wavelengths 576 and 579 nanometers. A characteristic mercury spectrum. And immediately after mercury, let's take a look at krypton spectrum, because at a cursory glance the krypton emission spectrum is quite similar to that of mercury. Krypton is an inert gas with atomic number 36, and if we take a look at its emission spectrum, we can find the green and yellow lines as the strongest emission lines, just like mercury. However, the prominence and frequencies of these green and yellow lines in krypton spectrum are quite different from that of mercury, and we can distinguish them with their wavelengths. The green lines in the krypton spectrum got their wavelengths at 520 and 531 nanometers, while the yellow line in krypton spectrum has its wavelength 568 nanometers.
Now, What is the mathematical explanation of these various spectra? Yeah, some primary teacher had derived this formula to explain the visible lines emitted from hydrogen atom. We will see how this formula gave rise to Bohr's theory of hydrogen atom, the very foundation of quantum mechanics. We will also check out some special spectra like that of alcohol, ammonia, cadmium, sulfur and many others. Stay tuned. So, thank you guys. Thanks for watching, and please do not forget to like, share, subscribe and press the bell icon. Thank you.